So my talk is about lane detection for autonomous driving, and I'm going to touch two approaches for lane detection. One is conventional image processing technique, whereas the second one is all about how convolutional neural networks can be applied for lane detection. So this is the content of my presentation. First, I'll give you a very brief introduction about lane detection, and then I'll talk about the main challenges to lane detection systems in general. And then I'll talk about the common lane detection methods. And then I will try to give you some detailed information about our approach that we have been developing here for our AutoDrive challenge, as well as part of the Access Lab. And I will talk about in detail about the conventional methods of lane detection, and then I have also the second method, deep learning based lane detection method. And at the end, I'll give you some very brief conclusions based on the presentation. Okay, introduction. So lane detection is obviously a very important building block for advanced driver assistance systems or for semi-autonomous vehicles. It's also a very important or key building block for autonomous vehicles. And for advanced driver assistance systems, lane detection is used as a lane keep assist, or just for warning the driver. Whereas in autonomous vehicles, lane detection can be used for steering wheel control, for lateral control, as well as longitudinal control. And in addition to that, lane changing can also be done based on lane detection system. So in general, when we drive our vehicles, we almost always need to be in the lane so that we can be safe, and overall we will have like a smooth traffic flow. So as you can see in this picture, all of the cars are driving in the lane, and if any one of the cars tries to go outside, obviously it will cause some trouble. So obviously, whether we're driving in highways or in urban roads, we must almost always be in the lane for our safety. So the point is, lane detection is really important for advanced driver assistance systems as well as for autonomous driving. Now, what are the challenges of lane detection? It's a very well-defined problem, but it's really challenging problem at the same time. So detection is really hard because of some environmental factors. And for example, lane markings or lane paintings may not be visible because of aging, as you can see in this picture. The right lane boundary is almost invisible. It's not that easy to detect it using a visual perception system. And sometimes the road texture can change. For example, in the second picture as well as the first picture, you can see the asphalt is not of uniform texture. And basically, when you set a threshold, it's going to be easily tricked by this change in texture of the road. In addition to that, lane boundaries are not always limited to these white or yellow paintings on the road. Sometimes the curves are also delimiters for a lane. So detecting a curve might be also very useful in order to successfully detect a lane. And the lane markings can also be covered by shadows, and this is really tough because when you try to process this image, the edges that you get from the lane boundary, because of these white or yellow lines, would be exactly the same as the age created by these shadows on the ground. So that makes the detection also very hard. And these shadows might come from buildings, trees, other cars, and etc. Sometimes in urban roads, you might also get this kind of other road signs, for example, a pedestrian crossing here, or maybe some directional arrows. Those signs can also interfere with the lane detection systems in general. And another really serious issue is lighting changes. For example, in the bottom picture, you can see there's a glare because the car is basically traveling from shadow to bright region. And in this instant, you may get this kind of glare. And obviously, there is a bright yellow line on the left and a white yellow line on the right. But because of this glare, it's not visible for the camera. And as a result, you get wrong detection. Especially this picture has got a lot of information. Imagine if you wrongly detect a lane boundary and try to go to the left or to the right. If you try to go to the left, obviously there will be some potential accidents. Even when if you try to go to the right, for some reason, if the car decides to go to the right, then will be also another problem. So these are the main challenges for lane detection. So what are the common techniques that are already developed and or under development for the detection systems in general? So in general, I think we can classify lane detection systems into two major groups or categories. First one, just until recently, everyone was focused on using conventional image processing techniques to find out the lane boundaries. And usually the white or yellow paintings on the road are the features to detect. And usually the most commonly used techniques rely on canny edge detector together with a half-line transform. And the canny edge detector is a very well famous edge detector. It's a very good detector. And basically it finds the edges in the image, and the half-line transform is a way to find line segments in that image. So by combining these line segments, it's possible to find the lane boundaries. Well, this technique is used in different ways, but mostly, majority of the techniques rely on these two detectors and transforms. Whereas the deep learning based method, which is kind of relatively new technology because of the advancements in these convolutional neural networks, recent publications focus on this deep learning approach. And the very popular ones are the semantic segmentation based, also instance segmentation, which is more or less similar. And there's also an end-to-end approach. In the semantic segmentation, basically, as you can see in this figure, the lane lines are, for example, in this case, colored white. And all the pixels that belong to the lane boundary must be labeled like this. And at the time of inference, you have to also classify each and every pixel in that image. So that's either a lane boundary or a lane marking or maybe a background or some other class. That's how the semantic segmentation works. And after finding those pixels that belong to a lane boundary, there will be some further post-processing to identify the left or the right lane boundaries. And instance segmentation, almost similar to semantic segmentation, except that in this case, it just gives you each instance of a lane. For example, in the second picture, colored in orange, green, and these purple colors, those are instances of the lane boundaries. And there's also an end-to-end approach. In this case, it just takes the image, this properly labeled image, and there is an associated either polynomial or some other curve that represents the lane boundaries. So without without any need of post-processing, it just generates the final result. Whereas semantic and instance segmentation requires some form of post-processing. Now, the issue with these conventional methods is that algorithms are developed based on manually tuned parameters, for example, thresholds, and because of that, when the lighting changes because of some other environmental factors, the thresholds or some of the parameter values will simply not work well. So it has got those issues, and it is kind of less robust. Whereas deep learning methods, seems that so far the results obtained from the semantic segmentation or instance segmentation methods, they seem to work really well. And the only issue is that they're computationally kind of intensive and very slow. Usually they don't fulfill real-time requirements for autonomous driving. And of course, without the GPU, it's unthinkable to use these semantic or instance segmentation methods for lane detection. On top of that, of course, the image must be labeled. Each and every pixel in the image must be labeled as a lane marking or a background or some other class. That's the relatively the concerns with these deep learning methods compared to the conventional methods. Conventional methods, on the other hand, they are faster. They are relatively faster. So now our approach, we developed actually two lane detection methods. As I said earlier, one uses the conventional method, and the second approach uses convolutional neural networks. And we try to develop a very lightweight convolutional neural network for lane detection. So here is our first lane detection approach, and these are the procedures or simply the steps that we followed to get the lane boundaries. And the very first step is simply pre-processing the input image. You get a stream of images from a camera, and each of the frames are kind of pre-processed. This pre-processing is kind of a generic term. People might add a lot of processes in this at this stage, but in our case, we just simply convert the color space of the input image into grayscale and the YCRCB color format. And grayscale image actually catches the white lane markings very well, whereas the grayscale may not properly or correctly capture the yellow colors on the road, especially when these yellow lines appear on the bridge where the texture is not similar to a black asphalt road. So where the CR channel or the difference between the CR and the CB channel captures the yellow paintings very well. So we combine this grayscale and the CR channel to get a better image that captures both the white and the yellow lines. The second stage is a bird's eye view transformation. Obviously, this perspective view doesn't really give us the scale, the measurements of the lane widths and the lane marking thickness and these details directly. So we transform the image from perspective view to a top view, so that we can make direct associations with the actual lane characteristics, like, for example, how wide is the lane, or how much is the thickness of the lane in terms of pixels, as well as in terms of standard units. So this is very helpful even later on to combine this visual perception result with map data or some other sensor data. So to do this transformation, we have to use either camera calibration information together with the camera orientation or location on the vehicle in order to come up with this transformation matrix. Or we can even find we have to find like 4 different points on the image so that we can generate the transformation matrix from the perspective view to the bird's eye view. So after we transform the image into a top view, we have a lane marking extraction method. This is a very important part of this method. We apply a Gabor filtering on this bird's eye view image. And the Gabor filter is almost the same as a Gaussian filter, except that it's modulated by a cosine or sinusoidal function. And Gaussian filter, Gabor filters have got additional parameters like this gamma, lambda, and phi for phase shift, wavelengths, and some orientation adjustment. So with these parameters, you can adjust the orientation of your filter, your kernel, and so that you can enhance the image very well. So for our case, we just picked 7x3, or you can even use 7x7 filter kernel. And as you can see, at the center of the image, we have a bright stripe or bright pixels. And when you go away from the center, the brightness or the intensity of the kernel reduces. So this filter size is selected based on the thickness of these lane markings, and so that we can get a better enhancement. If this doesn't match well with the thickness of the lane boundaries, we may not get a very good result, but still works okay. But this one is much better if it matches with the actual dimension of the lane lines. So the Gabor filtering, it's simple convolution. The kernel convolved with the image, the grayscale image, gives us an enhanced image like the one shown here. So if you closely look at this around the lane boundary, see that the white pixels are brighter than the grayscale image, and the surrounding pixels around that lane boundary are kind of, they're suppressed, or their intensity values are 0 or close to 0. So it's because of this convolution operation with the kernel. So this gives us a very good pattern on the filtered image. So if you look at a single row in this filtered image, this is the pattern that we get. And as you can see, these peaks correspond to the white pixels in this image, or basically the lane boundaries. And right next to these peaks, the intensity values around it are close to 0 most of the time. But in some cases, it may not be exactly 0, but it's going to be close to 0. So our lane extraction method tries to take advantage of these patterns. So this is the 3D plot of our processed image. And as you can see, these are the peaks corresponding to these lane markings. So this is the magnified image for a single peak. And these are just suppressed pixels. And because of this enhancement, the intensity value for each lane boundary might approach or close to 255, which is the highest value. So the next stage in the lane marking extraction process is to apply the lane attributes or the lane parameters. For example, thickness is one of the parameters in a lane. We know that lane boundaries have got specific thickness, and there might be some slight changes or variations, but usually the thickness is known and it's also measurable. And the second parameter that are part of or characteristic of the lane is that lane markings are brighter than the background. So we check the intensity value of the lane markings to separate pixels that belong to a lane boundary from the background. There's also average lane widths. Most of the time, of course, in our method, we assume that the lane lines are parallel. It may not be correct all the time, but I would say more than 90% of the time, this assumption is correct. The lane lines are usually parallel. So that means the width between two lane boundaries is kind of constant, and even in standard units, this is known. So we consider these three important parameters to find out which pixels belong to a lane boundary and which ones are not a part of the lane boundary. So this is the algorithm that we developed. Basically, at the first stage, we collect those pixels which are considered to have very low intensity, like this, shown by these arrows. And then the second block checks the thickness between these consecutive pixels having a very low intensity value. And if it satisfies this thickness, which corresponds to the actual thickness of a lane boundary, then it will be passed to the next stage. And the next stage checks the intensity value. And like I said, the lane boundaries are usually brighter than their background or the surrounding pixels. So we check that intensity. And the last stage is to measure the distance between the peaks, which corresponds to the width of the lane. So if those pixel points that satisfy these three requirements, then they are considered to be a part of the lane marking. So the last stage in this method is a curve fitting. Now we have all the pixels which are considered to be a part of the lane boundary. Now the last stage is just to fit it with a parametric curve or maybe a non-parametric curve. In this case, we used a Bezier curve, a third-order Bezier curve, which corresponds to a third-order polynomial. But in this case, it's just a non-parametric curve. So a third-order Bezier curve is given by this expression, and the parameters P1, P2, P3, and P4 are called the control points, and especially the parameter P2 and P3 determine the shape of the curve, whereas P1 and P4 are just simply the start and end points. So in order to find this P1 and P4, assume this is our output, filtered output, we divide this image into 4 sections, and we simply calculate the average intensity value for each section, and we simply assign those average values to P1, P2, P3, and P4. So once we get P1, P2, P3, and P4, we simply substitute these values in this equation to generate the interpolated values, and we get simply the lane boundaries. So that's the conventional image processing method for lane detection, and we checked our method with these 2 data sets. One is the Caltech famous data set, and the second one is Udacity data set. And for comparison purposes, we also implemented the famous Canny edge combined with the half-line transform method. And we created about 2,000 lane data for, just to quantify the accuracy of our method. So we simply count the true positive and the false negative results of our method or both methods, and we can easily estimate how effective this technique is based on this measure. So this is what the result looks like. For example, for the Caltech dataset, which in this case, the lane lines are usually straight lines, and a canny half transform based methods also work very well, whereas the solution that we proposed also works very much better than the canny half transform. Simply in this case, it works better because in some parts of this, there is some kind of curved lines, and in this case, the half line or the canny edge detection based methods may not work well for curved lanes. The Udacity dataset has got a lot of curves, and there are shadows on the way, and there's a texture change, and even there are some cracks in these roads, and the canny edge detection based usually generates a lot of edges, and it's kind of hard to find the lane boundary. So the canny half transform based method performs a little bit low in this data set, whereas the technique that I showed you earlier works really well. So that's the here's got the data set. Okay, so here is a video that we created for the Udacity dataset, and as you can see, it works very well most of the time. And this is also another video that we created. In this case, we have a center line, or the center estimate of the lane. And as you see, you might observe some oscillations. That's because of, on the left lane boundary, you have got dashed lanes overlapped with solid yellow line. And that somehow affects when we perform some kind of averaging and performs slight oscillation. That this should not be really a big issue if we actually use this for autonomous driving. So in this case, our method actually not only relies on this white or yellow lines, even if there are no lane markings on one side of the road, we can still find out where it should be based on the average lane width information. So in this case, red simply indicates that there is no lane marking detected, but this is just inferred based on what's detected on the left side. So that's our detection method. And performance-wise, actually this method runs from about 20 to 25 frames per second. And this is without any form of optimization. It's just direct implementation of that method. And this is tested on the Core i7 CPU with 4 cores. Okay, here's the second method, which is a deep learning method. And here is for comparison. What we're trying to do here is what if we replace all this pre-processing stage, the bird's eye view transformation, and the lane marking extraction, all these stages by a deep neural network. So as I showed you earlier, in the lane marking extraction method, we have a lot of thresholds, for example, for intensity, for lane widths, and things like that. So all of these parameters should be easy to learn by our neural network, and we shouldn't be worried about how we place the camera and what the intensity values should be and things like that. So as long as we provide enough data for our network to learn from, it should be able to capture the parameters used to extract the lane boundaries. So that's the idea behind it, and it should be a very simple process. So we have got a deep neural network. It takes the image and it generates the lane marking locations, and at the end we post-process simply, which includes a curve fitting, which I will talk about in detail later. So here is the idea. So simply consider a patch of the image as shown on in this image, and determine whether there is a lane marking in that patch or not. So as you can see here, for example, if you consider this patch here, there is a lane marking, and in this patch, for example, there is no lane marking. So we can create this patch starting from the left side of the image, and we can slide that patch, along the row, and we can search all these lane markings in that image, and later we can combine these detections to form the lane boundary. That's the basic idea. So the advantage of this approach is that you don't need to label each and every pixel, which is which is the case for semantic segmentation or instance segmentation methods. And of course, for classification at the time of inference, we don't need to also classify each and every pixel. We simply consider a patch and we say there is a lane marking or it's a background. So it's like a yes, no kind of result. So in order to do that, we came up with a simple convolutional neural network architecture. And what we want is that this neural network should be lightweight with very few parameters, and it should work reasonably fast even without a GPU. That's the requirement, because semantic segmentation methods, all those existing methods, they're really complex, and they have got so many hidden layers, and they usually work really, really slow. And it's almost unthinkable to use them in, to run them in a CPU. So contrary to that, we just want to have very simple, effective convolutional neural network architecture that works fast in a CPU. So for example, here we have got simple convolutional layers. The depths or the number of these layers might vary, but in our case, we consider it from 5 to 10. And we have a convolution, it's just reducing the size of the image, max spool layers, and additional convolutional layers. And finally, we have a classification layer. We just convert them into fully connected layers, and then we apply softmax to get the results, the confidence level, whether the given image patch has got a lane marking or whether it's a background or not. So this is a simple convolutional neural network, and here's how it works. So it takes an image patch from a given full frame, and then it that image patch pass through this network, and we get a result, either background or a lane marking. So if it happens to have a lane marking in that image patch, it will be considered for further processing. So instead of simply considering like the center of this image patch as simply the location of a lane marking, we actually want to be a little bit more precise in here. So we convert this image patch into a binary image, and we calculate the average pixel location for the lane boundary. So in this case, the green dot indicates where the average lane marking is. So this is a part of the post-processing. So if the given image patch has no lane marking, then it's simply ignored. So this is what the output looks like. So given this full frame, we start processing somewhere, we select region of interest. We don't want to go through the whole image. And for example, starting from here, we scan the image horizontally. And as you can see, the detected points are, the image patches are shown in this cyan color, and the orange dots indicate the average pixel location. So as you can see, it's clearly showing where the lane markings are. And as part of the post-processing, we simply collect all these orange dots and we fit them with a polynomial. So this is another image frame to show you that this deep neural network sometimes gives you wrong prediction, wrong inferences. For example, here, the edges of this guardrail or just on the bridge sometimes appears, or it's kind of similar to a patch with a lane marking. It's because of the contrast between this side and the lower side. Well, this is handled by the post-processing stage, removing false predictions. And in order to, again, facilitate the curve fitting as well as the direct measurements, we simply convert these points, only points, into a bird's eye view. But in this case, I'm also showing you the image itself in the bird's eye view, just to see where these detected points are on the image. But in practice, in reality, we don't need to transform this image, all of them. We simply transform the detected points, which minimizes computational effort. So for this technique, we created a training data set of about 40,000 image patches, among which 50% of which contains a lane marking, and the remaining patches have got simply background. Some of it has got vegetation and different kinds of background that we can see on the road. So using this training data, by the way, it's very easy to generate this training data with just a few images. You can have hundreds or thousands of image patches. So we trained the network, and of course we applied some post-processing and curve fitting, and this is what the result looks like. So as you might notice here, this technique is actually used to detect multiple lanes, at least 4 lanes and 3 lanes, or just 4 lane boundaries. Even the previous method can also be extended to do the same. This one is our most recent work, so that's why we extended to multiple lane detection. So our preliminary result shows that this method works about 10 to 12 frames per second on a Dell Precision laptop, and it has got Intel Xeon 8 core CPUs and 8 core CPUs, and of course there's also enough RAM in that computer and that laptop. The image size we considered is 1024 by 768 pixels. This is a relatively large image, and we can get even faster result if we reduce the image size by half, or instead of going through the image based on that image patch width, we can skip some rows in order to get much faster result. Of course, in doing that, when you try to gain speed, there is always a loss in accuracy. So there is that trade-off between performance, in terms of speed and accuracy. So this is the video, the previous video, but in this case we applied our convolutional neural network based lane detection. So as you can see, this one is much smoother compared to the previous result, and on top of that, we have also additional, adjacent lane detection as well. Okay, so in conclusion, I've already talked about the importance of lane detection. Obviously, we want to be in the lane all the time. Even autonomous vehicles are also required to be in the lane all the time. And I've also highlighted some of the challenges in the lane detection process. Although it's a very well-defined problem, because of those challenges, lane detection is in general a very tough problem. I also talked about two types of lane detection. One that uses traditional image processing approach, which relies on manually tuned parameters, and that makes them kind of slightly sensitive to environmental factors. And although some people try to use adaptive filters, it's still not that reliable compared to kind of these new deep neural network methods. Deep neural methods they might be slow, but they seem to work really well compared to the conventional image processing technique. Performance-wise, I already mentioned this. Conventional methods are usually faster. Of course, it depends on implementation, whereas deep learning-based methods are in general slow, and they usually require GPUs in order to accelerate the inference time. So that's all I have. I guess 45 minutes since I started. Thank you for your attention.